So this week, the plan is we're going to try to get through most of Chapter 2. Again, I think some of it will be review still, solving. We're going to look at some solving equations, solving inequalities, but there might be some things on the calculator that you haven't seen before. All right, so that might be some of the new stuff. Once we start to get into Chapters 3 and Chapter 4, then I think we'll be getting into some algebra stuff that may be less familiar. Sometimes it's topics you cover in Algebra 2, it depends on the year. You guys probably didn't get to it, just because of the way everything happened over the past couple of years. So I think pretty soon we'll start hitting some new stuff. Okay, so the first thing I want to take a look at is let's just type that in on the graphing calculator. All right, so 2x cubed minus 3x squared minus 3x plus 2. What I want to kind of focus on is how many times that graph crosses the x-axis. All right, and after a while, you'll kind of have an idea of how many times it could cross without even graphing it, just by looking at the equation. Okay, so let's see if we notice anything. 2x cubed, if you notice, my cursor is still up in the exponent. When you start typing the minus 3x squared, I need to press the right arrow, so I'm not in the exponent anymore. Minus 3x squared, minus 3x plus 2. Now, I'm not on a standard window. I should have probably done zoom 6. But this window is still good enough I can see how many times it crosses. And you should have a graph that looks roughly like that. And how many times does it look like it crosses the x-axis?
3.
3. Okay, it looks like it crosses 3 times. And if you look at the highest exponent, it's a 3. So that 3 is a hint at how many times it could cross. It doesn't have to cross 3, but it could cross up to 3. Another way to look at it is if you subtract 1 from that number, it tells you how many times the graph can turn. This particular graph has 2 turns in it. One up here, and then another one down in quadrant 4. Okay. So subtracting 1 from the highest exponent tells you how many times the graph could turn. Doesn't necessarily mean it has to turn that many, but it's a limit. Okay. So the graph crosses 3 times. And if I were to write down the coordinates of all 3 of those points, they would all have the same y value. What's the y value at any point along the x-axis, Mike?
0.
Yep, it's 0. So when you're finding an x-intercept of a graph, what you're really finding is a 0. You're finding a value you can plug in for x and then get 0 for y. That's what an x-intercept is. We call that a 0. We can also call it a root. So now, let me graph what I have in parentheses right there. Just going to keep what I already have in y1 and watch what happens. So 2x minus 1 and x minus 2. All right, and watch it as it graphs. And what's the difference between what I typed in the first, or what does it at least look like the difference is between what I typed in the first time and what I just typed in?
You factored it?
Okay, so this is factored. And how about in terms of the graph? How does the picture of the red one compare to the blue one I had? Yep.
It's exactly the same.
Yeah, it looks the same. I mean, we could prove it's the same by foiling this out. And it would work if you distributed this all out, you would get what we started with. So it's factored. Now, factoring it helps us to find the zeros easily. If you were to take this equation and set it equal to 0, it's very easy to figure out the values of x that make it 0 now. When it was written like this, if you were to set it equal to 0, not as easy. So think about if you multiply 3 things together and it equals 0. What must have to happen? If you multiply 3 things together and you get 0, what does that mean? Yep, Nick?
One of them was 0.
Yeah, one of them is 0, or two of them, or all of them. Okay, but the point is, if you're going to multiply three things together and get 0, at least one of them has to be 0. What could you plug in for x to make this first one 0? This first, we'll call this the first factor. Caleb?
-1.
-1. What could you plug in for x to make the second factor 0? Yeah. 1/2. And to make the third factor 0, you can plug in 2. The numbers that you plug in that would cause this factor, and that factor to come out to 0, those are called the zeros of the function. This particular function has 3 of them. -1, 1/2, and 2. Now, if we go ahead and try to find the exact solution on the calculator, watch what happens. Okay, I'll just do one of them. Let's do second calc 0. Have we done that before?
No.
Okay, so the calculator can tell you where the graph crosses the x-axis, as long as you type it in. I'm going to clear out the red one, just so I'm only dealing with the blue one. You could leave the red one, it doesn't matter. And to calculate where it crosses the x-axis, we're going to do second calc 0. You can't do intersect. Intersect is for where two graphs on the screen cross. So we want to calculate where a graph crosses an axis. An axis isn't a graph. That's just like the background. Right, so you're going to pick 0. And the way that it works is you're going to have to hit enter 3 times in different spots. First thing you have to do is pick a point that you know is to the left. I'm going to do the 0. I'm going to do this one over there. So pick a point that you know is to the left of the root you're trying to find. Pick a point that you know is to the right. Hit enter. And at this point, you should have these dotted lines on the screen. You've basically told the calculator, look between the dotted lines to find an answer. If there is only one place where it crosses the axis between the dotted lines, then the guess doesn't matter. Okay, so we'll just put the guess, kind of close, that's fine. And it tells us the answer is 2. X equals 2. And that's one of the roots to this equation. Now you have to do each one separate. You can't get all 3 roots at the same time. It'd be kind of nice if you could, but we'd have to do second calc 0 to find the next one, and then do it one more time to find the last one. Right, so let's answer the question. When they ask us something, you have to make sure we're answering it the way they want. It doesn't say here, write the coordinates of the x-intercepts. It says, find the values of x that make the equation equal to 0. So the answers here are not coordinates. It's just 3 numbers. -1, 1/2, and 2. If the direction said find the coordinates, then you would write -1, 0 in parentheses, 1/2, 0, and so on in parentheses. Okay, any questions on that? Now, getting that in factored form, that can be a little tricky. We're going to talk more about that in probably chapter 3. Okay. How do you factor something that's a little more complicated than a quadratic, okay, like a cubic. And you can only factor it if it works out nice. Like this one worked out very nice. The answers are rational numbers. As long as you can get rational answers, we can do it. When we start to get into irrational answers, that's a problem. So you might have noticed I keep using the words root. Sometimes I say 0, sometimes I say x-intercept. A lot of those terms are interchangeable. So if you find a number that is a solution to this equation, that means you can take the value, plug it in, and get an answer of 0. That number that you found, if you write it as that number, comma 0 in parentheses, that would be an x-intercept. If you just write the number by itself, that's called a root of your equation, or it's also called A0 of the equation. Tim?
What would happen if two of those would both have the same number to get to 0?
So you can end up with two that are the same. Like let's say you factored it and it came out to x minus 2, something like that. So in that case, 2 makes the first factor 0, 2 makes the second factor 0. We call that a repeated root. Or you can also, if you want to get fancy, it's a root of multiplicity 2. Multiplicity means how many times it occurs. And let's say you had a third factor, you factored into 3 things that were the same. Now the root there is 2, and it occurs, it has a multiplicity of 3, meaning it happens 3 times. So that kind of goes back to that idea that the highest exponent tells you how many times it could cross the axis. Doesn't mean that it has to cross that. This particular graph, if you were to type it in, would only cross the x-axis in one spot, at the number 2. It wouldn't cross more than once. Okay, so let's kind of take a step back to the simplest kind of equation that we can have that crosses the x-axis. That's a linear equation. And if you wanted to get x by itself in that equation, I just put the box around, what would be the 2 steps to get x alone? Yeah, Nick?
You subtract d from both sides and divide by a.
Exactly. So if you're looking for the root, or you're looking for the value that makes that equation 0, to find it, you would minus the b to the other side, and then you would divide by a. Now, can a line cross the x-axis more than once, assuming a non-horizontal line? What do you think? Can a non-horizontal line cross the x-axis more than once? Yeah, John?
Yes.
Okay, can you give me an example?
The x-axis?
Yep, the x-axis.
I don't know how to write it, but it'd be like a line going this way, or like this way.
So remember, line has to be straight.
Yeah.
Okay.
It would be like like a sign, essentially, you know?
Like a wave?
Yeah.
Well, this does cross more than once, but that's not a line.
Oh.
It has to be straight. So can a line that's not horizontal cross the x-axis more than once? Mike?
No.
No. Right? No matter how you, I mean, if it's horizontal, it could be right on the axis, but if it's vertical, it's only going to cross once. If it's on a diagonal, it'll only cross once. Right? That's why I wrote the solution, the only solution, is negative b over a. Did you have another question, Michael?
Nope.
Nope. Okay. All right. So if let's solve that for x. Okay. And Caleb, when I get x by itself there, what do I get for my answer?
It would be -3/2.
-3/2. And Madison, what do I call that again? That's the what of this equation?
Solution.
The solution, and specifically it's the solution that makes the equation come out to what? 0. So that is called the root. Okay, that's the root or the 0 of the equation. Write it in the coordinate format. There's your x-intercept. Okay, let's go up kind of one notch here. We've gone from linear, now to quadratic. Sophie, how many times can a quadratic equation cross the x-axis?
2.
Yeah, it could be 2. If you had a graph that looked like this, where you could flip it over, it still could cross 2 times. Is there any other situation that could happen besides crossing twice? Yeah?
It can turn 1.
Okay, it could turn, well, this one turns once too, right? It just comes down, and then it takes a turn, and it goes up. So can you explain more what you mean?
Oh, well, I thought you just meant like what in the equation. What does the equation tell us about the graph?
So yes, so we could have 2 roots or 2 zeros in a graph. Is there any other situation besides having 2? Like, could we get 3? Could we get, yep?
You could have 0 or 1.
You could have 1 or 0, yep. You could have 1 if it kind of just comes down, touches the graph, and goes back up. That would be an example of 1. Or you could have none if it was a parabola, and it could be right side up or upside down, that never crosses the axis. So any one of those situations can happen. And we talked about this last week. A quick way to tell if you have a quadratic equation, how many times it crosses the x-axis. Look at those 3 numbers. And you do this calculation, b squared minus 4ac. There's 3 things, or 3 different results you can get. B squared minus 4ac can come out negative, can come out 0, or it can come out positive. If it comes out negative, when you do b squared minus 4ac, negative means you have this case. You have no roots. Okay? Well, I should say it this way. You have no real roots. You would have imaginary. If b squared minus 4ac comes out to exactly 0, you have this case. That's where the axis, where it touches the axis and goes back up. If b squared minus 4ac comes out positive, you would have this case, meaning it would cross the x-axis twice. Right? So if it comes out positive, crosses twice. If this comes out to the number 0, it crosses once. If this comes out to a negative number, it does not cross at all. And I think that was, we did that back in, I don't remember the exact section, it might have been 1.3, 1.4, one of those sections. Okay, so this says to solve, and it does say approximately, which means a decimal is fine, which means we could use the graphing calculator. If it said to solve as an exact answer, we would have to do what? How could you solve this and get the exact answer? Yep.
Could we move the 2x squared to the side and set to 0?
Yeah, we'd set it equal to 0, and then what would you use from there once you got it equal to 0?
To b squared minus 4ac.
So that would tell you how many roots there are, but that's part of a bigger formula that would give you the actual answer.
Oh, the b plus or minus the square root of negative b minus 4ac divided by 2a.
Negative b plus or minus the
Yeah.
square root of b squared minus 4ac all over 2a, yes. And what is that called? Anyone remember? Yep, Caleb?
Quadratic formula.
Quadratic formula. So if you want an exact answer, you got to use quadratic formula. If you want an approximate answer, calculator is okay. All right, but I am going to do what Tim said, is I am going to get it equal to 0 because we're calculating zeros. So that's always the first step. Let's get that equation equal to 0. And because I'm used to factoring problems like this, I like to have the x squared term positive, so I'm going to move everything to the left. It's not wrong if you move everything to the right, you'll still get the same answer. But let's put everything on the left. So 2x squared plus 2x minus 1 equals 0. Now if we want to quickly get an idea of how many times it's going to cross the x-axis, you can almost do that in your head. B squared minus 4ac. I don't even need to finish it. I know a negative minus a negative is a positive. That's a positive answer. So I can tell you this graph will cross twice. So that's helpful because if we set a window and we only see it cross once, we did this calculation, we know it should cross twice, we need to zoom out. We need to find the other answer. All right, let's type it in and see what we got. So we got 2x squared plus 2x minus 1. 2x squared plus 2x minus 1. I'm going to do zoom 6 just to set my window back to normal. And let me make sure I typed everything in. 2x squared. I know it should cross twice, so that was a hint to me. I typed something in wrong. because I wasn't seeing it cross at all. 2x squared plus 2x minus 1. Let's try it now. There we go. Okay, so now I can see it crosses twice. And Maddie, can you tell me how I would find where it crosses on the left? Let's do this one.
Like on a calculator,
Yep, on the calculator.
second calc,
Okay,
0,
all right. And what do I do now?
move it to the left.
Okay.
Press enter,
Then press enter. Yep,
then move to the right, press enter.
to the right. Press enter. Okay.
And put your guess in the middle.
Yep, let's put the guess kind of close. And we get about negative 1.37. And that's approximate, which is fine. So we could call that x, well actually we won't call it x1. We'll just say x equals 1.37. Or, second calc 0. Pick a point left. Pick a point to the right. Do your guess, and we get 0.37. So those are my two roots, or my two zeros to this equation. Write them as a coordinate, and you could have your x-intercept. Questions on that? So we don't have to do this. The old way of finding roots was you had to zoom in. We have a feature now, we can automatically use second calc 0, but on some older calculators, this option isn't there. So if it wasn't there, what you'd have to do is keep zooming in to where it crosses the x-axis, and then the more you zoom in, the better estimate you can get. But we don't have to go through that process. So this is the feature that we've been using. We're just calculating the root right on the calculator. So let's try this one. Let's do one more. Before I graph this, how many times could this graph cross the x-axis? Yep, Maddie?
3,
It could cross 3. I could cross 2, or it could cross 1. It can't cross 0. We're going to learn that odd degree polynomials, which this one is, degree 3, odd degrees go up and they go down forever, and they're always connected. Well, if you go up and down forever, and you never lift your pencil, you're always connected, you're going to go through 0 at some point. Okay? Even degree polynomials do not go up and down forever. Think of a parabola. It can either go up or down. It doesn't do both forever.
How would you solve this without a graphing calculator?
So to solve this one without a graphing calculator, you could do one of two things. There is a formula called the cubic formula, like the quadratic. The difficulty, it's not that it's hard, it's that it's long. It's just, there's a lot of stuff in the formula. It's not fancy math, but it's a lot of adding, subtracting, squaring, all that stuff. So you could use what's called the cubic formula, or if we're lucky, we would have one root that comes out rational, which means you could write it as a fraction, like 1/2, 1/3, 2/3. As long as you can get one root that's rational, we can then use what's called long division or synthetic division, and then we can turn this cubic into a quadratic. But you have to be able to find one root that's rational. If there was no root in this problem that you could write as a fraction, and you didn't know the quadratic, the cubic formula, you wouldn't be able to solve it. So let's do the same thing we did with the quadratic. And very quickly, I'll be able to tell you if this is a problem you could do without graphing. Okay, let's graph it and see what the answers look like. So we've got x cubed plus 2x minus 1. Zoom 6. It looks like it could be an answer that you could solve without the calculator. What does it look like the root is pretty close to? Yeah?
Around like 1/2.
It looks like it's around 1/2. I'm not sure I don't know. I'm not really sure if it's going to be 1/2 or it's going to be like 0.47 or 0.52 or something like that. If it is 1/2, then we could do this without the graphing calculator. Let's see. I have a feeling it's probably not going to be exactly 1/2. I can actually check if it's 1/2 quickly by going to the table. Maybe it is. Type in 0.5. No. When I typed in 0.5, I did not get 0. So 0.5 is not the root, which means this is not a problem we could solve without the graphing calculator unless you know the cubic formula. So we're going to do second calc 0. You're going to go left, right, and enter. So it's 0.45. Okay, any question on that? All right. So, third degree polynomial. So we looked at linear, looked at quadratic. Let's look at cubic. So, a cubic has the form ax cubed plus bx squared plus cx plus d. A, B, C, and D can be any real number you want, except A can't be 0. What would happen if you plug in 0 for A in this formula? Yeah, John?
It would become fine afterward.
It would become a what?
It would become not a cubic.
It would, yeah, it wouldn't be a cubic, it would be,
What was it?
Yeah.
That one.
it would be a quadratic, assuming B isn't 0. Then if B was 0, then it would be linear. Okay? But as long as A isn't 0, any of these other ones could be 0. In fact, the simplest cubic you can have is 1x cubed. B is 0, C is 0, D is 0. And of course, that's a problem you could solve very easily by hand. So that's a cubic equation. If I gave you this, all you have to do is take the cube root of both sides, and you have your answer. When cubics start to get harder to solve is when you have more of these terms in there. Right? Then it gets harder to solve. There is another method for approximating roots. We don't really talk about it too much in this class. It's kind of like a fancy guess and check method, but you can actually set it up in like a Google Sheet or an Excel spreadsheet. Basically, it kind of starts out like the graphing calculator. You pick a value that you know is lower than your root, and then you pick a value that you know is higher than your root. So let's say we had a root that crossed, I don't know, let's just do it like this. 0, 1, 2, 3. And our graph looked like this. So we could pick a value that we know is lower, okay? 0. So we start with the low value of 0. Then we say, okay, pick a value that's higher, 2. Then what you do is you average them, okay? So you find the average, and the average is 1. So what we do now is we say, okay, is that new value higher or lower than the root? It's lower. Okay? That becomes my new low value. Okay? So this is like, that was the first step. Okay? So now my low value is a 2. My low value is a 1. My high value is a 2. I average them again. 1.5. Then we say, okay, is that higher or is it lower? Whichever one it is, it's going to replace the previous low or high value. In this case, 1.5 is higher. So my low value stays at 1. My high value is 1.5. And now I would average them again. 1.25? And then we keep doing this. And in a spreadsheet, all you have to do is highlight that row, drag it down to like 100, and it'll do this 100 times. And then very quickly, you'll get an answer that's pretty accurate. And if you're like, well, how can you tell if it's higher or lower? Well, you have a formula for this. All you have to do is plug in that number to your formula, and the spreadsheet can do that. So if the formula was like y equals x cubed plus 2, or something like that, just plug in 1.25 for x and see if it comes out negative or if it comes out positive. If it comes out negative, it's lower than your root. If it comes out positive, it's higher. But it's a very quick way to find a root. You just need a starting point that's lower and higher, and then you keep averaging it, and you get more and more accurate. Okay, but not a method that we really use. And I don't know if that's how the graphing calculator does it. I don't know if that's the most efficient way to find a root, but that's similar to what the graphing calculator probably does. When it finds a root, it's not doing any algebra. It's just guessing and checking really fast. Maybe it's doing a million guesses in about a second. So it can get a very accurate answer pretty quickly. So third degree polynomials, they can turn up to 2 times. Sometimes they only turn once. It depends. Well, I mean, sometimes they don't even turn at all. They kind of have this little bit of a curve, and it looks like it wants to turn, but it never really does, and it just keeps going. All right, so they can either turn twice, or they can turn not at all. They can't turn once, because turning once would mean that's like a parabola. Okay, that's a parabola. All right, so let's see how many solutions this equation has. So we've got x cubed minus 5x squared plus 6x minus 1.
What's x cubed plus or minus?
I think it was x cubed minus 5x squared. Is that what I typed in? X cubed minus 5x squared plus 6x minus 1. Okay. All right, how many solutions does it look like this equation has? Yeah, Nick?
3.
3. Sometimes you have to zoom in a little bit, especially if it's close. But this one, I think especially if I make it a little bigger, it's pretty clear that it does cross in 3 spots. So this one had 3. Is there any question on how you would find one? Like if I asked you to find the middle one? Any question on how to do that? Your second calc 0? Okay, so we'll skip that then, because we've done a lot of them. All right. And that's 2.2. So the last thing we're going to look at is part of section 2.1, I'm sorry. Now we're going to look at part of 2.2, which involves a little bit of stuff on the calculator again, a little bit of algebra, but I don't think there'll be anything new on the calculator or algebra-wise in this section. So whenever we're solving a problem, pretty much every time it involves making some type of equation. And then sometimes once we have that equation, we solve it with algebra. Sometimes we solve it graphing. Okay, different ways we can solve it. But usually there's some algebraic component to every word problem. You have to set up some type of equation. So we're going to look at a problem that's about investing money. And we've got a person that's going to invest money. He has an amount of money, and he's going to put it into 2 different investments. All right, so Bill's going to invest $20,000. And the 2 investments are the same type of investment. They're investments that pay what are called simple interest. And we're doing that because the formula for it, as the name sounds, is pretty simple. So he's going to invest some of the money at 6.75% simple interest, and the remainder of the money at 8.6% simple interest. Now, of course, if you can invest money in something, it's always better to invest in something that's going to pay you more money. You can make more money. So you might say, well, why doesn't he just invest all his money at 8.6? Well, maybe there's a limit. Okay, there's certain accounts that will pay you interest, but only up to a certain limit. There's a checking account out there that pays 3% interest, which is pretty good, but they only pay it up to $15,000. You can put more money in the account, but you won't make more interest. So you're better off to put your money somewhere else. So maybe that's what's going on here. So two different investments, each of them pays simple interest. That's the formula for simple interest. Okay, and that is something you would need to know. I equals PRT. In fact, this is a very good problem to know for Friday. So I stands for interest. P stands for principal. Principal just means the amount of money you're investing. R is your rate. But very important, we write the rate as a decimal. So don't, like if the rate is 12%, don't plug in 12. Plug in 0.12. And T is the time, usually measured in years. So what they want us to find here is an equation that represents the amount of interest Bill would earn in 1 year. And to start us off, they give us this information. Assume that Bill invests X dollars at 6.75%. What is this in my formula up above? The X dollars, Michael?
P.
P, that's my principal. It's how much money is being invested. Okay. How many different investments is Bill putting his money in here? 2. He's splitting it up into 2. He's going to earn interest from each of them. So he's going to earn some interest from investment number 1. He's going to earn interest from investment number 2. What are we going to do with the 2 different amounts of interests he earns to find the total? Yep, Madison? We're going to add them. So let's start out by finding how much interest Bill earns at 6.75%. Interest equals principal times rate times time. Okay, Michael just said this is my principal. That's how much money is being invested at 6.75%. How about my rate? I know it's 6.75%, but how would I write that in my formula? Yep, go ahead, Mabel.
Would be 0.0675.
Yep, 0.0675. There's my rate. And the time. How long is Bill doing this investment for?
1 year.
Just 1 year, so we don't need that. So let's just simplify that. Usually when we multiply a letter and a number, we put the number in front. So 0.0675x. All right, so there's the interest at 6.75%. Now, let's do the interest at 8.6. Again, principal times rate times time. Well, the time is 1 year again, so I'll fill that in. What's the principal this time? How much money is Bill investing at 8.6? We got to take into account what he already did. Okay?
The principal, that is going to be X minus an investment from the first one.
So we have $20,000. So can you tell me what's left to invest at 8.6?
20,000 minus X1, or
X. So he already invested X dollars before. So what's left now? 20,000 minus X. Leanne, what's my rate in this case when I put it in the formula?
Maybe 0.086.
Good. 0.086. Let's distribute that out just to simplify a little bit. So we have 20,000 times 0.086 gives me 1720 minus 0.086x. So there's my interest at 8.6%. The total is when we take box 1, box 2, and add them, and combine any like terms we can. So we're going to have 1720, and then I'm going to do 0.0675 minus 0.086, because when I add them, we're adding a negative, so it's really subtracting. All right, so we got 0.0675 plus negative 0.086. Negative. So that gives me negative 0.0185. Negative 0.0185x. And if we want, because we are going to do something with graphing, we could write it like this. Why did I do this? It's the same thing, but any thought why I rewrote it that way? Yeah.
put it in slope intercept form.
Yeah, I wanted you to recognize it as slope-intercept form. So when we're setting our window, you can see you got an intercept up over 1700. We're going to have to set the y max pretty high. So before we graph it, there's a difference between graphing that equation that I have under the total interest, just as an algebraic equation in slope-intercept form, compared to looking at the graph of our actual problem. What would we not want to look at in this problem if we're graphing it to actually visualize the problem and not the algebraic equation? Yeah? Yeah, we don't really want to look at negatives. Yes, the graph does go in the negative direction, but we don't care about negatives. They don't make sense. So we don't want to look at negative interest, because this isn't an investment where you can lose money. And we don't want to look at negative investment. We don't have a negative amount of money to invest. So let's use the graphing calculator and figure out how much money Bill invested for each investment if he earned $1,509.10 in interest. So let's see if we can figure out first where that's going to go. So he earned a total of $1,509.10. Let me go back to my formula for a second. Where is that going to go in my total interest formula, Tim?
On the left of the equation.
Yeah, it's going to go on the left-hand side. It's going to go right there. We're going to set the total interest formula equal to that and solve. All right, so we have $1,509.10 equals. I remember the y-intercept was 1720, but what was the slope again?
Negative 0.0185.
0.185x. All right. So we know we're going to have a y-intercept at 1720. We're going to have a horizontal line at 1509. So we're going to graph two different things here. And what are we going to look for once we graph it? We're going to graph the left in y1, we'll graph the right in y2, we'll hit graph, and then what are we going to look for? Yep. Yeah, we're going to look for where they cross. Okay, we're going to look for where they cross. I'm sorry, chew, I call it. So we're going to look where they intersect. Now, if we put everything on one side and get it equal to 0, then we could calculate a root. Okay, but if we want to do it the way it's set up here, we'll do 2 graphs and find where they cross. So we've got 15, 09, 0.1. You don't have to do 0.10. You can do 0.1. That's fine. Negative 0.0185x plus 1720. All right, so earlier Mabel said we don't want to look at negatives, so we don't have to look at that. What about x max? What should I set my x max to? There's definitely an x max in this problem. There's no like negotiation on what x max should be. It has to be something specific. Yep, John?
So the x max would have to be greater than the y-intercept, right? No?
No, it's x max is totally independent of that.
No.
And it has to be an exact number. So sometimes I say you can use different things, not in this one. Lindsay?
Is it 20,000?
It's exactly 20,000 because that's how much money we have to invest. So if we want to see a full picture of the problem, we have to go to 20,000. Y min, negative interest, doesn't make sense. But we do want to go above 1720. Maybe 1800. I think that'll be enough. So there's the line representing how much interest he earned. There's the equation for total interest. And we're going to see where they cross. Second calc intersect. Enter, enter, enter. And I think have we done the intersection before? People remember that? Have we done second calc intersect on the calculator before?
Mm-hmm.
Yep. Okay. So then the intersection here is 11,400. That's x. And what was that again? X is 11,400. That was the amount of money.
At 6.75. Or no.
Let's go back up. So X is the amount of money at 6.75%. Yep, that is correct. 6.75%. And what would you do to figure out the amount of money at, was the other one 8.6? Yeah, 8.6.
20,000 minus 11,400.
Yeah, and that's going to come out to, I think, 8,600. That's how much money he invested at 8.6. So just be careful, especially if they only ask, well, even if they ask for both of them, that you don't mix these two numbers up after you've done all that work. Remember which one is which. And that was defined way back at the beginning, right there. Question on that one? All right, let's look at our last question. And I think we've looked at a question like this before. In fact, I think we've done this exact question in homework. But it says to consider all the rectangles with a perimeter of 100 inches. Find an algebraic representation that describes the area in terms of the width. So we're going to have a rectangle. And they're basically telling us what to pick for the variable. They want this formula to be in terms of the width. All right. I've labeled the right-hand side as W. Is there anything else that I can label easily in this rectangle? John? We can do length, but we're gonna have to think about that one a little bit. Tim?
Perimeter.
The perimeter, so we know the perimeter is 100, yep. Now, any other side that's pretty straightforward to label?
So,
Yeah.
it's a rectangle, the other width has to be proportional.
And what is it?
It's W.
Yep. So we have W. Now we need to label the top and the bottom. But we want it in terms of the width. We don't want to introduce a second variable here. You don't need a second variable. You only need one. So let's assume like this 100 inches was something we were making like a fence out of. What do we have left to use? We've already used a certain amount. Think of how much you've used. Think of what you started with. Tell me what's left. Nick?
Would this be P equals 100 minus 2W?
So the amount of material we have left right now is the amount we started with minus what we've used. W and W make up the sides. How much of this material has to go on top, and then how much of that material has to go on the bottom? Yeah? Half of it. Right? It's a rectangle. So you're going to have 50 minus W as the length, and 50 minus W as the width. So find an equation that represents the area in terms of the width. So area as a function of width. Somebody tell me what would go right there. Yeah?
It would be 2W times 100 minus 2W.
So what's our formula for area of a rectangle? Or, yeah, just area of a rectangle.
I mean, not the 2, just length times width.
Length times width. What's my length here?
W
W stands for,
width.
that's my width. So what's my length?
50 minus W.
50 minus W. And my width
W.
is W. There you go. There's a formula for the area as a function of the width. And you could multiply that out. Negative W squared plus 50W. So what's going to end up happening is it's a parabola, and putting a negative in front, we learned last week that reflects it. So it's going to look like this. So let's see if we can find a complete graph. So we've got negative, remember you have to use the variable x on the calculator, plus 50x. 20,000 is way too big for my width. What's the biggest that the width could possibly be here? Think of what number could it get close to? John?
25, right? Or no.
It can go bigger than 25.
Yeah.
But there is a limit on how big the width could be. Tim?
Has to be less than 50.
Has to be less than 50, right? It could be 49, could be 49.9, as long as there's a little bit left to make the other two sides.
Oh, okay.
All right, so it has to be less than 50, so we'll just put in 50. The thing we don't know is what's the biggest area that we can make. Well, let's put it at 800 and see if we can see the top of the parabola. Okay, but by setting it 0 to 50, you should see the parabola perfectly on the screen. It should start in the lower left, and it should end perfectly in the lower right. Okay, so there's our problem. And that curve represents all the different areas that you can have. They didn't ask us to find the maximum area. That's usually what this type of question asks for. So all you have to write down for this is your window. Specifically, x min and max, y min and max.
How did you get 800?
I just guessed, but I mean technically we already kind of know the answer to this kind of problem. What's always the best shape? It's always a square. So I know if I were to make a square with a perimeter of 100, it would have to be 25 by 25. So I knew the best area would be 625. So I picked something a little higher. But if I didn't know that, I would just pick a number for y max, and if it went off the screen, pick a higher number. Okay. All right, so that's 2.1 and 2.2, part 1. So you guys have a little under 20 minutes or so left. Let's put up the homework. Page 82 is from 2.1, okay, finding zeros, and page 88. I think page 88 is really three or four questions. 31 to 34, I think, is an interest problem, so they're all connected, like the one we did a little while ago. And then 21 to 23, I think that might be a rectangle one. So those are kind of all the same question as well. All right, we've got a little bit of time. If you want to start that, you can. If you want to check in with me and see what you got right and wrong on last week's test, now would be a good time to do that as well.